listeners, get ready, because we are diving deep into a book that's truly cosmic. Stephen Hawking's A Brief History of Time. And hold on to your hats, because we're talking about the updated and expanded version with all the good stuff on wormholes and time travel. Just like you asked for.
I have to say, I'm already hooked.
You and me both. And to help us make sense of this cosmic masterpiece, I've got a true expert in astrophysics and cosmology joining us for the ride.
Thrilled to be here.
Now, even Hawking himself was blown away by how popular this book became. I mean, the guy joked about outselling Madonna. Can you believe that?
Well, I think it really speaks to that deep-seated desire we all have to grasp those big existential questions, Where did it all begin? What's our place in all of this? Is there some grand finale to this cosmic show we call life? Or do we just sort of fade to black?
That's it exactly. And for many people, A Brief History of Time was their first real peek behind the curtain of these big mysteries without getting bogged down by complex equations. It's kind of like how this deep dive will give you those key insights without needing a PhD.
I like that analogy. Approachable knowledge. That's what we're going for.
Speaking of approaching knowledge, the book kicks off with this great anecdote about an astronomer giving a lecture. They're explaining, the basics. Earth goes around the sun around the galaxy, Astronomy 101.
Right.
And someone in the audience just chimes in with that classic line, "It's turtles all the way down."
Ah, yes, like that old myth about the Earth resting on a giant turtle. And of course, what's holding that turtle up? Another turtle. It's a fun way to illustrate how we used to explain the universe with stories and beliefs, rather than what we now consider, scientific evidence.
So instead of galaxies and black holes, we had an endless tower of turtles.
Pretty much.
But eventually, folks like Ptolemy came along and tried to inject a little more, shall we say, logic into our cosmic understanding, right?
Exactly. Ptolemy's model was all about the Earth being the center of everything. Sun, moon, planets, stars. They all revolved around us in perfect little circles.
Sounds cozy.
Well, almost perfect circles. To make their observations fit this Earth-centric model, they had to invent these things called epicycles. Imagine little mini-circles on top of the regular orbits, all to force the math to kind of match what they were seeing in the sky.
So, kind of like those old sparagraph toys. Except, instead of cool geometric patterns, you get the entire universe. Seems a bit overcomplicated, don't you think?
It was incredibly complex. But here's the kicker. Even though it was fundamentally flawed, Ptolemy's model actually worked. Well, okay, for a while. At least it was useful for predicting where things would be in the sky.
And I imagine it was pretty convenient for everyone at the time because it lined up perfectly with the whole Earth is the center of creation idea.
Precisely. It fit in nicely with the dominant religious beliefs of that era. But as with all scientific models, it was destined to be challenged, poked full of holes, and eventually replaced with something more accurate. And that's exactly what happened as our understanding of the cosmos grew and evolved.
Oh, it absolutely did. And it's amazing to think that those early models, flawed as they were, really pushed us to question more, to observe more closely. And that questioning led to, some pretty radical shifts in our understanding of the universe.
Radical is an understatement. We're talking about completely flipping the script on centuries of established thought, right?
Exactly.
So how did we go from a universe that revolved around us to, everything we know today? It took some seriously brave thinkers to challenge the status quo. Take Copernicus, for example. He had, and it was radical back then, idea that maybe, just maybe, it was the sun, not the Earth, that sat at the center of the solar system.
Whoa. So instead of everything revolving around us, we were actually the ones doing the orbiting.
That's the gist of it, yeah.
Talk about a reality check.
You could say that again.
Yep.
But Copernicus, whether he knew it or not, really set in motion this incredible scientific revolution. And then along came Galileo with his trusty telescope, and all of a sudden, boom, we could observe the universe in a whole new light, literally.
Okay, Galileo. Now, there was a guy who knew how to make a statement. Pointing that telescope at the heavens, he found evidence to back up Copernicus's heliocentric model. Right.
Absolutely. He saw the phases of Venus, which, if you think about it, only makes sense if Venus is orbiting the sun, not the Earth. And then there were the moons of Jupiter, these celestial bodies just dancing around another planet, proof that not everything revolved around us. It was a game changer, a real paradigm shift.
It's pretty mind-blowing when you think about it. That point in history when a new technology, in this case the telescope, opens up these whole new ways of seeing and understanding the universe. It makes you wonder what incredible discoveries are still out there, just waiting for us to develop the tools to perceive them.
I think about that all the time. It's what drives me.
Me too. But before we get too far ahead of ourselves, there are two big players in the world of physics that we need to talk about: relativity and quantum mechanics.
Right. These are the twin pillars of modern physics. Relativity governs the universe on its grandest scales. Gravity, black holes, the large-scale structure of the cosmos. And then you have quantum mechanics, which reigns supreme in the realm of the very, very small. Think atoms, subatomic particles, all that good stuff.
Okay, so on one hand, we've got relativity, courtesy of course, the one and only Albert Einstein. That's all about gravity, those massive objects warping the fabric of space-time. I always picture, like, a bowling ball on a trampoline when I think about that.
Perfect analogy.
And then there's quantum mechanics, the wild world of subatomic particles, where things get all fuzzy and uncertain. Honestly, it's enough to make your head spin just thinking about it.
You and me both. But it's also what makes physics so fascinating, the fact that we still have so many mysteries to unravel.
Totally. Okay, but back to relativity and quantum mechanics. How do we even begin to reconcile these two seemingly contradictory theories? I mean, they both work so well in their own domains, but they seem to clash when you try to bring them together.
That, my friend, is the million-dollar question. It's something that physicists are still wrestling with today. But let's try to break it down a little bit, starting with relativity. As you mentioned, it's all about gravity and how it works on a large scale. Basically, the more massive an object, the more it warps the fabric of space-time around it.
Right, like that bowling ball and the trampoline. So a star, for example, would create this kind of dip, this curvature in space-time that planets then orbit along.
Precisely. Now imagine, if you will, rolling a marble across that trampoline. That marble, representing an object traveling through space, would follow the curvature caused by the bowling ball, right?
Yeah, totally.
Well, that's essentially how gravity works according to relativity. It's not some mysterious force pulling objects together, but rather the curvature of space-time itself telling those objects how to move.
Okay, I think I'm starting to get it. But what about time? You keep saying space-time. Does that mean time itself can be warped and stretched and squeezed too?
You got it. Time is not absolute, it's relative, meaning it can be experienced differently depending on your speed and the strength of the gravitational field you're in. The closer you are to a massive object, the slower time runs for you relative to someone who's farther away.
Wait a minute. Are you saying that if I hung out near a black hole for a while, don't recommend it, by the way, I would actually age slower than my friends back on Earth?
That's the general idea, yep.
Time travel and anti-aging creams, all thanks to relativity. Sign me up. But okay, let's move on to this other mind-bending theory we were talking about, quantum mechanics. This is the realm of the really, really small, right? Like way weirder than even the wonkiest parts of relativity.
Oh, absolutely. In the quantum world, particles can act like waves, and waves can act like particles. Everything exists in this hazy state of superposition, meaning they can be in multiple places at once, at least until we try to actually observe them.
So it's like the universe is playing hide and seek with itself.
Kind of. Quantum mechanics is definitely not for the faint of heart.
No kidding. Okay, so just to recap, we've got the universe writ large, where gravity is king and space-time itself gets all bendy. And then there's this quantum realm, where things are fuzzy and uncertain and just plain bizarre. How did Hawking even begin to make sense of these two seemingly contradictory ideas? So we've got these two powerhouse theories, each explaining the universe in these wildly different ways. Did Hawking seem to think they could ever really, I don't know, play nice? Or are relativity and quantum mechanics destined to be like that couple that just argues at every party?
Well, Hawking actually seemed pretty optimistic about finding some common ground. He believed that a theory of quantum gravity, one that could unify these seemingly opposed worlds, was within our reach.
Quantum gravity, that's like the holy grail of physics, right? Unlocking the secrets of the universe for the tiniest particles to those massive cosmic structures.
Exactly. It's the ultimate goal for many physicists.
But where do we even begin to look for something like that?
It's a journey that takes us to some of the most extreme environments imaginable. Think the singularity at the heart of a black hole, or the very first moments after the Big Bang. These are places where our current understanding of physics kind of breaks down, where gravity and quantum mechanics collide head-on.
Okay, so we're talking some serious cosmic heavy hitters. But before we get lost in a black hole, I have to ask about one concept that really blew my mind. Hawking radiation. It's like black holes aren't just these cosmic vacuum cleaners sucking everything up. They actually radiate energy.
It's true, and it's one of the most amazing discoveries in modern physics. But to really get it, we have to dive into the strange world of quantum mechanics and something called virtual particles.
Hit me with it. What are virtual particles, and what do they have to do with black holes?
Okay, so picture the vacuum of space, right? It's not actually empty. It's buzzing with these pairs of virtual particles that constantly pop in and out of existence.
Hold on. Particles just popping up out of nowhere.
Well, they borrow energy from the vacuum, exist for this incredibly short amount of time, and then annihilate each other, returning the energy.
So it's like the universe is constantly giving out these tiny loans of energy and then collecting on them almost immediately.
That's a really great way to put it. Now imagine this happening near the event horizon of a black hole. That point of no return, right? Sometimes one of these virtual particles gets pulled across the event horizon while its partner escapes.
Kind of like a cosmic game of tag, where one particle gets caught and the other makes a run for it?
Exactly. Now, the particle that falls into the black hole, that's it for that particle, gone. But here's where it gets really interesting. The particle that escaped, the one that's now real, carries away some of the black hole's energy with it.
Wait, so black holes are losing energy. They aren't these, like, eternal, unchanging objects.
Nope. That slow trickle of escaping particles is what we call Hawking radiation. It means black holes actually have a temperature, an incredibly low one, but still, and over ridiculously long periods, they slowly evaporate.
Mind blown. So simple yet so profound. But after this incredible journey through a brief history of time, what's one big takeaway you think every listener should walk away with?
I think Hawking summed it up beautifully when he wrote that our thirst for knowledge, our drive to understand the universe, it's what makes us human. And while we've made incredible strides in unraveling the cosmos, there's still so much out there, so much we don't know.
It's that feeling of standing at the edge of the unknown, looking out at the vastness of space and time that really captures the imagination. It's what makes this journey so compelling, so awe-inspiring. And Hawking leaves us with this final, thought-provoking question. Even if there is only one possible unified theory, it is just a set of rules and equations. What is it that breathes fire into the equations and makes a universe for them to describe?
It takes us beyond the equations, beyond the science, to this almost spiritual realm of meaning and purpose. It makes you wonder.
It really does. What a journey this has been. We've explored the tiniest particles and the largest structures in the universe, grappled with time and gravity, even contemplated the fate of black holes. I hope you found it as fascinating as we did.
It's been a privilege diving into these big questions with you.
And to all our listeners, until next time, keep looking up at the stars and never stop asking why.